Is okay. Alright, finally got it started up. I'm gonna get some music rolling per usual, and then we're gonna do some AC analysis. I'm not all that competent in AC analysis. I have a lot of I have a lot of work to do and much room to be better. And so that's what we're going to do is we're going to develop our skills in AC analysis.
Hey, Rec Boy shit, you know what?
Except that that little bit may very well ruin my stream and give me copyright issues. Oh well. Okay. It's taking forever. Alright, fantastic. Is it gonna stay? It's not staying. Now it is. Okay, I'm pulling up the problems now. Alright, a little bit of like phasor manipulations, right? We have to be able to turn the equation into its phasor. Phasor form, I guess we could consider it to be a form, like, right, what would you call an equation which describes the function in this manner? A form. So the phasor form, and then there's a rectangular and there's a polar, correct? And then the other form would be a time dependent. Yes, the current in a 20 millihenry inductor is right. So we can consider okay, 20 millihenry inductor. Right? Can we see that? Fantastic. The current in a 20 millihenry conductor is equals 10,000 T plus 30 amps. Okay, very well. Calculate the inductive reactance. The reactance. So XL equals omega L equals 10,000. Is that really it? There's no 10,000 T. That is very well it. 10,000 omega L. 10,000 multiplied by 20 millihenry. E to the negative 3 equals. Well, I mean, 10 e to the 3, 20 times 10 is 200. So 200 ohms, right? It's a reactance, XL. And then it asks for the impedance of the inductor. The impedance Z equals J XL equals J 200. Right, let's just put it like that. Okay. The phasor voltage V. The phasor voltage. The phasor voltage, indeed. Cosine. Well, VL of T as a function of time equals the inductance multiplied by the derivative of the current with respect to time. Right. So that is true. That is true. So I guess let's go ahead and find the derivative of our initial function. IL equals, we already know this is 20 millihenry. $10,000, 10 cosine, sine negative. Right, cosine of the derivative sine is negative sine. 10,000 T, 10,000 multiplied by 10. One more. Yeah, so 100,000. 1, 2, 3, 4, 5, 6. Yeah. 1E6. Sine 10,000 T. Okay. Plus 30 degrees. Amps. Okay. And now, so 20, -3, negative would be 1,000. 1 times 20 would be 20,000. So 20E3. 20,000? Really? Yeah, 20 times -1. Negative 20. Would it not be? But also, would that be the case? So, okay. Now, if I add 90 degrees to this in order to make it a cosine, like, does that change the sign? The sign of it. Let me look this up. Yeah, sine 90 degrees plus theta equals cosine theta. Exactly. And it's just sine though, right? So there's no negative. It'd be cosine plus 90. It'd equal negative sine. Cosine theta plus 90. Okay, negative. Alright. But anyways, so plus 90 would be positive. Yeah, sine. Yeah. Let me double check. No, I don't have my calculator. That's awful. I guess I got my phone calculator. But we figured it out. Let me see. 20e to the -3 multiplied by what, -1. 1e6. $10,000 multiplied by 10. 1e6. 1, 2, 3, 4. Yeah. But it should only be 5. Because that's 4. We only add 1, 5. It shouldn't be 6, 5. Okay, that would make it 2. Wait, so make it 2. 1, 2. Yeah, so it'd be 200. No, 2,000. 5. That would leave 4. 1, 2, 3. Alright, that would. Fuck. Ah, shit. Times 1. E5. Right, 2,000. Okay. Shit. Cosine. No, yeah. From sine to cosine. Cosine 10,000 T plus 90, 30, 120 degrees equals 2,000 20,000 2,000 multiplied by, or no, 2,000 phase 120 degrees. Okay, right. So now after we calculated that, because we're looking for a function for the voltage, 120 degrees. Okay, yeah, let's see. 2,120 degrees, yeah, volts. Let me put my units. Let's not forget our units, absolutely very important. Okay, now the last question, the steady state expression for the voltage across the inductor. The steady state expression for the voltage across the inductor. Yeah, that's pretty much it, but okay. So it would equal 2 cosine 10,000 T plus 120 degrees kilovolts. I guess it's like the most formal way to write it. I don't know. The question again was steady state expression. Okay. Let's move on to the next one. 5 microfarad capacitor is okay. And we have it's 30. Four thousand T plus 25 degrees. Okay, we got a 25 degree out of phase, and we got a cosine function volt. Okay, calculate the capacitive reactance again. So XC equals J, that's our imaginary number, divided by omega C. And this would equal J divided by 4,000 multiplied by, what is it? What is our capacitance? Oh, I didn't specify. 5 microfarads. 5 e to the negative 6. Okay, so, well, 1, 2, 3. That would be 3, that would be 3, that would be 5 times 4, that would be 20. E3. So, 2,000. Alright, 2,000. 20 E3. 20 E4 is, again, right? Oh, it'd be negative though. It'd be negative 3. Wait, so 1, 2, 3. Whatever, 1 divided by 20 e to the negative 3, 50. Okay, equals 50 J. Is this correct? Negative 2. Yeah, negative. Yep. Negative. For the capacitor, it's a negative. Okay, 50. Imaginary number. Okay. All right, cool. Right. Okay, so that's just simply the reactance. So now, reactance. Okay, the impedance of the capacitor. Okay, actually, the reactance XC. XC equals just negative 50. Is it negative? It is, yes. 50 ohm. Negative 50 ohm. And then this is the impedance, right? As you see. Negative 50 J. The steady state impedance. The phase voltage. Phase voltage VC equals. I forget how we write phase. I think it's capital. No. There's no negative. It's an amplitude of 30, phase 25 degrees. Right. 0.6, 115. The phasor voltage. The phasor voltage. What would I need to change? 0.6. It's a fraction, and we have some added number. What do we have now? 20? Yeah, that would be. Add 90 for what reason? It says the phasor voltage. Wait, the phasor voltage I? Oh man, it must mean current. It literally, there's Dino was good. Welcome to the chat. Welcome to the stream. Thank you, everybody. Say something in the chat. Anyways, it literally says the phasor voltage, but then it has a symbol for a current next to it. Get a load of this, Dino. An error in the homework questionnaire. This is completely unacceptable, but we figured it out. Let's solve for the current. Okay, so the current's going to be, we have the equation for the voltage right here. 30 cosine 4000 t plus 25 degrees. Okay, and so the phasor, this is incorrect. VC is, no, it's asking for I. So the current, I see, this is what we're looking for. This is indeed what we're looking for. Okay, let's figure it out. Okay, so I equals I. What does I equal? I equals C dVC dt. Yes, equals. Okay, what is our capacitance? 5 microfarads, that's right. So 5e negative 6. Alright, multiplied by, let's see, xc. 30 cosine. 4000 t plus 4000 4e3 multiplied by 30 negative sign 4000 t plus 25 degrees. Okay, yeah, just like this, amps. Okay, so 4e, whoops, oh shit, can you see? You should get more credit for finding errors. You find a lot. Oh yeah, absolutely, yeah, imagine that, they give me a little bit, some points back for finding every error, but I mean, I don't know, I never bring it to anybody's attention anyways. Absolutely, find a lot. Sure, everybody does, though, you know. Maybe somebody's talking about it. I'm not that kind of guy. Okay. 5e to the negative 6 times 4e3 multiplied by 30. Yeah, 0.6. 0.6. Okay, negative sign. We're gonna add 90 degrees to convert it to a cosine. But it's still gonna remain positive, so it's still negative. Regardless. So negative cosine 4000 t plus 25 plus 90, 115 degrees. Alright, now to write it in the phasor form, right? This is a time-dependent form. To write it in the phasor form, we just simply need the amplitude, angle, 115 degrees. And let's see. That's correct, although the answer should be positive. Why, though? Sine, it must be this relationship. But sine plus becomes positive, negative sign. I don't think that's the case. DVC. Is there something else I could have done? Like what about the voltage divided by the reactance? Wait, so 30, I don't know if it would have worked like that. I don't know. It would. We could have literally done, yeah, but but it's imaginary. So there's no real parts of it. But the imaginary part would it not be? We could have literally wrote this out also by simply just doing VC divided by XC. No. I mean, it'd be the impedance ZC. 30 cosine. That gave us 0.6. But what about this? We'd still need to take the derivative, would we not? So how would that be avoided? Because we're not accounting for the imaginary and how that would shift the phase. Is that what we're considering? Well, if we have that, that is the answer. Yet I still don't understand why is it positive. Why is it positive? Did I miss no? The going through. I don't know, I still don't see it. Alright, and then we have that expression, the last part of the question. Find the impedance ZAB in the circuit. See and express ZAB in both polar and rectangular form. Okay, interesting. Much more interesting. Alright, we're back in it. We're back in it. We're back in it. Okay. Alright, we got our equation here. We've essentially broke this down into our series and our parallel, and parallel again in series with this right here, blah, blah, blah. You know, this sort of sequence of logical analysis, right? We break it down, we break it down. All right, here we are. Then we have this long equation that we are just going to plug into our calculator that I need to go grab right now. Give me one moment. Okay. All right, I got my calculator. This is going to be way better. See that, yeah. $30 minus 40. Well, we'll say J. For engineer's sake. For engineer's sake, we'll say J. Okay. Find the impedance of the circuit in both polar and rectangular form. That's rectangular. This is rectangular form, and this is accurate. And then I think polar form would look like the square root of 30 squared plus 40 squared. Angle inverse tangent of 40 negative 40 divided by 30. Is that degrees? I meant squared. Okay. Equals. Wait. $50. That's correct. Okay, 50 angle inverse tangent function of negative 40 divided by 30, which is the ratio of the sine versus cosine, right? Okay, and that is correct. Okay, negative 53.13 degrees. Bang. Okay, that's in phasor form, but it's a that's polar coordinates essentially, polar form. And then this is the rectangular form, 30 minus 4j, which is EAB. Another one. Word up. Yep, there it is. Alright, let's solve. Wait, YAB. That's what it's called. Oh, the admittance. Okay. Okay. Millisiemens. Or rather, we could just take the inverse. Well, why? I mean, this works. And then I think can just inverse this. So let's put this in. Let's crunch these numbers. Sixteen minus 12 I minus 12 J. There it is. Okay. Do I need to be a little bit faster? Maybe we can try this a little bit faster. Wait a second, though. Oh, yeah. Wait. So, 1 divided by 16. Oh, yeah. Okay. Milla. Yeah. Okay. I got it. So, taking the inverse of this because we want the admittance, which, like, what is the... What's the symbol for admittance? Let's see. Oh, it really is the letter Y. Oh, yeah. Okay, and then we use Pythagorean theorem essentially to solve for the magnitude of the admittance. Essentially with respect to time, using these rectangular coordinates. Well, I guess it's just a polar conversion. It's just a conversion into polar coordinates, is it not? Okay. That's exactly what we're about to do then, right? And to acquire the magnitude, we use the Pythagorean theorem here. And then the phasor angle, the phase angle is going to be the inverse tangent function. And of course, y over x. Millisiemen. And then inverse tangent of 30 divided by 40. Yeah. Degrees. There we go. Beautiful. Beautiful. Okay, moving on to the next. The frequency of the source voltage is adjusted until V out is in phase with IG. Okay. What is the value of omega in radians per second? it's a tricky question. The frequency of the source voltage in the circuit is adjusted until V out is in phase with IG. What is the value of omega in radians per second? Pussy. Oh no. Oh no. I have to fix something. There we go. Okay, that's much better. That's exactly how I wanted it to be at the beginning of the stream. I can't believe I did not notice that until this very point. Alright, getting back into it. Brother. Alright, figuring out the total impedance. But I'm missing that, yeah. But that's the thing, that's depends on the frequency. It wants us to solve for the radians per second. Okay. And what? It would be... Okay, so the frequency of the source voltage in the circuit is adjusted until V naught is in phase with IG. What is the value of omega in radians per second? So if our voltage is in phase with our current or whatever, our current is in phase with our voltage, therefore there's not going to be any phase shift. And if that's the case, then we're only experiencing purely resistive impedances. Therefore, like, we shouldn't take into account either of the other branches, just 5K. Okay. Is my logic incorrect? I mean, like, what's happening here? Come on. Um, I don't know. So somebody help me out. Like, what am I missing? I mean, I'm supposed to find the radians per second, right? Omega equals 2 pi f. But I know nothing about the frequency. Other than maybe a frequency that would make this 0 and that 0. Or at least close to 0. Not him. Make him high, super high. Infinite. Yeah, I gotta solve for this variable omega. Let's do it like that. Yeah, let's do it up here. Now I have to decide something to multiply this by to get the same equation, the exact same, yeah. So a multiplied by 5e equals so 5e so all right,